Thus, the resultant channeling along the wall may be accentuated by vapor condensing because of column heat losses. Another cause of maldistribution is the packing geometry inhibiting lateral distribution. Void variations due to packing being improperly installed can also cause maldistribution. And then, the alignment with respect to the vertical can also cause maldistribution. There is no definite equation to compute for the efficiency of packed column. To gauge the efficiency of the column, HETP, or the height equivalent of the theoretical plate, is determined. To arrive at the expression for HETP, we first consider the mass transfer unit relationship from the two-film model. It is given by HOG is equal to HG plus lambda HL, where HOG is the height of an overall mass transfer unit, HG is the height of a gas phase transfer unit, lambda is the slope of the equilibrium line or the slope of the operating line, and HL is the height of a liquid phase transfer unit. HETP is then related to HOG by the equation HETP is equal to HOG multiplied to ln of lambda over lambda minus 1. The determination of HG and HL is vital in the determination of HETP. A lot of expressions for HG and HL may be used, and each of them incorporates mass transfer coefficients for the liquid and gas phases. The correlations based upon a large quantity of data for a variety of packings with gas absorption and desorption using water and organic solvents have been presented by Onda et al. This gas phase correlation also includes data on the vaporization of pure liquids. Included in the correlation are the following data. In the correlations presented by Onda, the parameters to be computed are the actual interfacial area between the phases and K, or the mass transfer coefficients. So these are the correlations presented by Onda. These correlations for the determination of the mass transfer coefficients look really bloody. The application of these equations can really be cumbersome. The expressions presented earlier are for the mass transfer coefficients. So this one is the expression for the wetted surface of the packing. If you are going to use the correlations, these are the parameters that you should consider. Although the equations look really hard, these parameters are actually given in literature. So the problem will probably occur in looking for these parameters in literature and inconsistent use of units. So let's try to solve a sample problem. Calculate Hg and HL for the absorption of SO2 from air into water at 87 degrees Fahrenheit and 1 atmosphere. For the conditions, GV is equal to 210 pounds per R-feet squared, GL is equal to 8,205 pounds per R-feet squared, S is equal to 4.76 feet squared, and 1-inch ceramic brass shed rings. From literature, we get these values. For SO2 in air at 87 degrees Fahrenheit and 1 atmosphere, μV is equal to 0.044 pound per feet, raw V is equal to 0.0726 pound per feet cube, AV is equal to 0.5 feet squared per R. R is equal to 0.7302 atmosphere feet cubed per pound mole runtime. T is equal to 87 plus 459 or 546 runtime. And then AV is equal to 58 feet squared per feet cubed from table 16.1 of Faust. Substitution of the values to the equation for the mass transfer coefficient of gas, we get Kg is equal to 0.379 pound moles per R feet squared atmosphere. Then solving for the wetted surface area, we get AW is equal to 37.3 feet squared per feet cubed. Now calculating for the mass transfer coefficient for the liquid phase, we get this value. And then calculating for Hg, we get finally, calculating for HL, we get this value. As what you can see, knowledge for the expressions for Hg and HL in terms of the mass transfer coefficients is vital in this process. There is an indirect relationship between HETP and efficiency. Packing efficiency decreases as HETP increases. Efficiency increases when the packing surface area per unit volume increases. Also, efficiency increases as the particle size decreases or as the size of the channel narrows. Another factor that can affect HETP is if the packing surface is better distributed around a random packing element. The distribution of the liquid and gas streams can also affect HETP. Other factors that may affect efficiency are the L/V ratio or lambda, pressure, and physical properties. To predict the value of HETP, the following methods may be used: mass transfer models, rules of thumb, and data interpolation. These methods are rather tedious and will not be discussed in this video. So after discussing packed columns, why don't you go ask for some help from Johnny? And I know you'll learn a lot more from her. So thank you.